Good afternoon, professors and judges. Today, I would like to present my mathematics research report to all of you. The topic of my research is starting from combinatorial geometry. I will mainly focus on 4 areas: the reasons why I chose this topic, the related examples, the result of my research, and my future aims in mathematical research. Firstly, there are mainly 4 reasons why I chose combinatorial geometry. First, I'm interested in the ideas of packing and covering, so I would like to explore more about it. Secondly, I find out a lot of interesting examples and theories from the 2 books listed in the PowerPoint. One of the books provides geometric approach to prove algebraic results, and I find it very challenging and intriguing. In fact, some proofs of difficult problems in combinatorial geometry can be easily understood by people of all ages. That's why I chose it. The approach mentioned just now is based on a theorem listed. In the theorem, we can eventually find out the maximum distance between 2 unit lattices is the root of 2/3/3. And this theorem leads to 2 inferences. In the first one, suppose fxy satisfies the listed condition. As you can see, we can show that there must be 2 integers, x prime and y prime, where at least one of them is not equals to 0. Then fx prime y prime will be smaller or equals to 2/3/3. This can be done by constructing another unit lattice. And for inference 2, we should make use of the theorem and inference 1 to show that there must be infinite sets of xy satisfying the conditions. For the approach of inference 2, the symbols and notations are quite challenging, in which we spent nearly 1 hour to understand the whole proof. However, I find it very interesting and would like to do a research on it. I'm amazed that people can use geometric approach to prove purely algebraic results. In the whole paper, I have mainly focused on 3 things: covering, packing, and Ramsey theorem. In inference 3.1, by arranging the squares of area 3 in descending order, we can eventually prove that the sum of x1 to xn is greater or equals to 1. However, if the total area of the squares is smaller than 3, the statement will become false. On top, inference 3.2 requires us to prove that there must be 2 points with same color and distance 1 when 3 colors are used to paint a region. The proof involves geometric construction techniques by rotating the rhombus ADGE about A to form FG, which is equal to distance 1. I will discuss it in details in the next part. Let's move on to my research area. In the paper, my aim is to show that for any triangles, a person can use 3 colors to paint every point on the plane, so that the triangle formed by 3 vertices having the same color will not be congruent to the original one. I've tried many ways to start with the proof. Firstly, I considered using a triangle by filling in the plane with parallel bars of different colors. We should determine the smallest possible height for a given triangle ABC, and then draw 2 parallel lines to enclose the triangle inside, where the distance between L and L1 is smaller than AD. Referring to figure B, AC will have a length exceeding 4 similar regions in the plane, so that we can easily find a triangle with vertices of the same color congruent to the original one. So my proof is wrong. Secondly, I have considered a hexagonal plane. The aims of shading is to maximize the distance between the first one and the second one. The ways of shading is to put 2 and 3 near 1, so that there are no 2 ones putting exactly next to each other. Suppose we fill the central one in the plane as 1, we can easily fill in the whole plane with either 1, 2, or 3, in which the line between 2 and 3 must be painted with either the same color of region 2 or the same color of region 3. Same principle applies to the whole figure. Firstly, I think we should draw a line starting from the bottom edge of 1. Then, construct a right-angled triangle with AB slightly exceeding 5 cm, in which I can use the Pythagoras theorem to find the length of AC. Hence, by rotating, we can also get that AB prime will be shorter than AC. So, the line will lie inside the hexagon 3, but not exceeding it. Consider AD will be greater than 5.01, and applying the same concept, we can see B prime will be lying inside hexagon 3, but not another one. However, the above proof is wrong due to a wrongly set assumption at the initial stage. If we choose to construct a line as the rod, the starting end of the rod is not valid and not fixed. It can be started from any places in hexagon 1. Also, the length of the rod cannot be valid and limited and can be extended to any length as I like. So the above proof is wrong. Recall what I have introduced in inference 3.2. Triangle ABC, BCF, ADE, and DEG are all equilateral. As F and G must be in the same color, so suppose AB equals to BF and it equals to X as well. And we rotate the rhombus ADGE until FG equals to X. By swinging the rod, we can easily find a line segment with length X, and the vertices are of the same color. Therefore, my proof is also wrong. Despite my incorrect proof, I get some results and findings. Firstly, I successfully find out that if the ratio of the shortest to longest height of the triangle is smaller than 1 to 2, then I have completed my proof. My basic assumption is that the line labeled 1 should be filled with color 1, line labeled 2 should be filled with color 2, and so on. Suppose the base of the triangle is located at the top of region 1. As you can see, the maximum location of the vertex will lie on the top of region 3. Therefore, I can conclude the ratio required must be 1 to 2. Secondly, I think that if we want to solve the question completely, we should think of some geometric shapes to separate AB in a figure, where the distance of AB is extremely short, while the distance of AC is roughly equal to the length of BC. Actually, for this, I have even observed how the border between two bricks are colored and filled, and I have thought of using octahedral shapes for proving. However, as octahedral shape cannot fill up a plane completely, so I get lost again. Also, I thought of using parallelograms and geometric transformation techniques. However, it failed as well. In fact, combinatorial geometry can be applied to our daily lives, such as the incident structures like construction of buildings and hyperplane arrangements. Also, it is useful in lattices and discrete groups or in chemistry. And lastly, it can be applied into architectural studies too. Therefore, my topic is related to our daily lives, and I think we should appreciate the beauty of mathematics starting from learning more about combinatorial geometry. Finally, I would like to talk about my future aims. Of course, I will try my very best to complete the proof of my current study. Also, I believe the questions can be solved by simple geometric methods, just like the examples listed above. But apparently, more have to be done. On top of this, I really hope to have chances and opportunities to receive further education in mathematics so that I can do more research in it, so I can acquire more knowledge and a more logical mind to tackle the unsolved problems as shown in the PowerPoints as A and B. By doing so, I hope to make contributions to the world, particularly in the field of mathematics. I would also like to pass on my passion in mathematics to my peers and fellow counterparts, first arousing their interest towards it. I would like to use this opportunity to express my sincere thanks to the principal and teachers of my school, and also my teacher advisor, Mr. Cheng, for his support and help for me to finish this research paper. Here are the mathematical paper references that I have referred to when doing the research report. Hope you all enjoy my presentation today, and thank you very much.